Welcome to example number 13. In this example, we are looking at the planet Mercury, which is shown by this little black dot that is revolving around the sun in an elliptical orbit. You can barely see here, there is a little bit of an outline for a sun, so maybe just I'll color that in yellow here. So before we jump into the actual problem part of it, let me just help you visualize what's happening with an animation. And let's also answer some of these questions like what's happening to the mechanical energy, the kinetic energy, and the gravitational potential energy as the Mercury revolves around the sun in an elliptical orbit. To help you visualize this problem, I'm using this particular app called My Solar System, and it's available from the PhET website, this little interactive simulation. You could change the masses and the velocities and so forth. So I decided to have two bodies. Body 1 is the sun here with a mass of 200 units. Body 2 is the mass of Mercury. Technically, this body should actually even be much less than that. It should be like 0.001. I'm not going to really make much of a change. It's just basically the sun is not going to move. And this body is going to be given a certain velocity here so that when I press play here, you can see it follows a path that is actually not circular. It's an ellipse, right? The point where it is the closest to the sun is called perihelion, and the point where it is furthest away from the sun is called aphelion. So to answer some of my conceptual questions that I had on your paper, I asked, what is happening to the mechanical energy of the system? And hopefully you realize that the total amount of mechanical energy remains constant, right? Energy cannot be created nor destroyed. Really what you have here is just kinetic energy and gravitational energy. Yes, the kinetic energy is definitely changing. As you can see here, when you get to this location, the perihelion, it's going much faster, so you're increasing in kinetic energy. And then when you get down to here, you're going much slower, so you have less kinetic energy. So it's gaining kinetic energy here and losing kinetic energy there. As it gains kinetic energy over here, it will be losing gravitational potential energy. And as it moves further away, it's going to be gaining gravitational energy. But the total amount of mechanical energy remains constant. Okay, so let's label some of the known information that we have. We have at perihelion, we're given this location right in here. That distance, which is labeled r sub p, is given a value of 46 million kilometers, or 4.6 times 10 to the power 7. Then at its furthest location called aphelion, we're labeled that distance as r sub a, and that's 6.98 times 10 to the power 7 kilometers, or roughly about 70 million kilometers away. We're also told the orbital speed when it's at the closest point, v sub p, is given as 59 kilometers per second. We are not given the velocity at aphelion, so we need to find that out. Furthermore, we're given the mass of the sun, m sub s I'll call it, for mass of the sun. That's 1.99 times 10 to the power of 30 kilograms. We also know Newton's universal gravitational constant, which is 6.67 times 10 to the power 11 Newton meters squared all over kilograms squared. So how are we going to solve for the velocity? If you recall from my discussion earlier about energy, we know that the total mechanical energy remains constant. So to solve this problem, we need to use a conservation of energy method. The energy initially, let's say at perihelion, must be equal to the energy later on at aphelion. Those two energies are equal to each other. Now if you recall, mechanical energy is really equal to the sum of the kinetic energy and the potential energies. In this case, we only have gravitational potential energy. So we have kinetic energy at the perihelion plus the gravitational energy at perihelion must be equal to the kinetic energy at aphelion plus the gravitational energy at aphelion. And we can now substitute our formulas in for kinetic energy and gravitational energy. Our kinetic energy is 1/2 the mass of the planet, little m, times the velocity at perihelion squared. The kinetic energy at aphelion would be 1/2 mass of planet Mercury, again, but multiplied by the velocity at aphelion squared. The gravitational energy formula, if you recall, we derived that earlier, is a negative g mass mass of this body, which is the sun, the mass of Mercury, little m, divided by the distance at that particular location. So at perihelion, it would be r sub p. Then we have the gravitational energy at aphelion, which is g times the mass of the sun times the mass of Mercury divided by r sub a, which is this distance in here. If you notice, there is a little m in every single term. That means you can cancel out that mass here and here and here. The mass of Mercury is not needed to solve this problem. Now you can go ahead and make some substitutions, but there is a common mistake people make here. You see, G is in newtons times meter squared over kilogram squared. And a newton, by the way, is equivalent to a kilogram times a meter per second squared. So your distances cannot be in kilometers. They must be in meters. And your speeds must not be in kilometers per second, but must be in meters per second, because you're using this constant of g here. So you need to convert those appropriately. So substituting in here, we will have 1/2 times the velocity at p, which is going to be 59,000 meters per second squared. Then we have negative g. I'm just going to put this negative in front of the whole expression. And then the mass of the sun divided by the distance between the sun and the planet Mercury, which is going to be 4.6 times 10 to the power 10, because we don't want it in kilometers, we want it in meters. So we're going to have to raise that exponent up to a power of 3 more, which is 10. And I'm seeing I'm running out of room. I'm going to just shift things over a little bit. And then I have 1/2 velocity a squared plus all these substitutions. And everything's the same except for this denominator here. It's going to be 6.98 times 10 to the power 10. And so the rest is just plugging it into your calculator and solving for the velocity of a. Plugging this all into your calculator, you're going to get 1/2 velocity a squared is equal to 7.57 times 10 to the power of 8. And then multiplying by 2 and taking the square root of that, I get an answer of 3.89 times 10 to the power of 4 meters per second, which is equal to also 38.9 kilometers per second. Okay, that's it for example number 13.